Hello, my name is Emina Sameli. I'm in grade 12, and today I'll be explaining a concept in calculus called optimization. Now, a lot of people might think that optimization is a very difficult topic to cover, or maybe they've heard that from an outer source, but the reality of it is that once you break everything down into steps, it won't seem as scary anymore, and maybe you might enjoy solving optimization questions just as much as I do. But before we explain the concept of it in calculus, let's first discuss what optimization generally means. In a general sense, optimization comes from the word optimize, which means making the most out of something given that you have restrictions. Optimization shows that your resources are finite, meaning that you don't have a never ending amount or supply of something, and you have to make the best out of it. As for the definition in calculus, optimization is defined as finding the most or least amount of something given that you have constraints or restrictions. And here we can see that both definitions serve the same purpose. So now that we've got a general hand of definitions, let's start to uncover optimization's fundamentals. Optimization focuses on two equations throughout, the first being the primary and the second being the secondary. The primary equation, as stated here, is p is equal to x multiplied by y, where p is the largest possible outcome. As for the secondary equation, it's just as stated, s is equal to x plus y, where s stands for the sum of x and y. And in this graph, we can see that since optimization is defined as the largest value of something, it's going to be the peak of the graph here. So it's going to be the largest possible value of y in terms of x. Now that we have that idea down, let's move to our examples, where the first one states, find two positive numbers where the sum of the first and twice the second is 64, and the product is a maximum. What I like to do is first I start off with identifying what the example is asking of me. So here it says find two positive numbers where the sum of the first and twice the second is 64 and the product is a maximum. Based on this information, we are going to write two equations, one for the primary equation and one for the secondary. So here we have two positive numbers where the sum of the first and twice the second is 64. So it's going to be 64 is equal to x, which is the first, and then twice the second, which is 2y. And then after that, we have the product is a maximum, and just as previously stated, we're going to be using p is equal to x multiplied by y. Now that we have this information, let's get to solving. So I'll keep these in frame for reference. We're going to start off with rearranging the secondary equation into an equation that we can use. So it's either you leave x on one side or y on one side. Either way, you are going to be getting the same values. As for me, I find it easier to turn this and leave x by one side. So it's going to be x is equal to 64 minus 2y, or it could be negative 64 plus 2y. Either way, since there is a negative sign, the overall value of the number shouldn't be affected. And then what we're going to do with this equation, is we're going to substitute it into the primary equation. So we have p is equal to x times y, so it's going to be p is equal to y multiplied the equation that we set for x, which is 64 minus 2y, 64 minus 2y. And then this, by using the distributive method, we're going to get 64y minus 2y squared. After that, since we have the equation for p, what we're going to do is we're going to find the derivative for this equation. So, as we wrote, p is now equal to 64y minus 2y squared. And so, p prime is going to equal to 64 minus 4y. So what we did here what we did here to find the derivative is multiply the power by the coefficient here. So 2 multiplied by 2 is 4, and then subtract 1 from the power, which leaves you with minus 4y. After that, what we're going to do is, since we have p prime now, what we're going to do is replace p prime with 0. So this is going to be 0 is equal to 64 minus 4y, and then by using simple algebra, we're going to leave y on one side and then try to find the value of y. All right, so it's going to be 4y is equal to 64, and then we are going to divide both sides by 4, and then we're going to get y is equal to 16. Okay, so keep this y value in mind. After that, what we're going to do is use the second derivative test, which is p double prime is equal to, since p double prime is equal to -4, it's going to be less than 0. So it's going to be less than 0, which makes it concave down. All right, so it's this downwards U shape, which means it's a maximum. All right, this is just to prove that this, as stated, the product is a maximum. So we used the second derivative to prove that. After that, what we're going to do is find the value of x now that we're given y. So, as we previously mentioned, here we have an equation for x, which is x is equal to 64 minus 2y. So let's write that down. X is equal to 64 minus 2y. We're going to substitute the value we got for y, which is 16. So it's going to become x is equal to 64 minus 2 multiplied by 16. Overall, it's going to be equal to 32. Now, if you're wondering whether or not the value is going to be correct if you switched x and y, whether the answer is going to be correct, it's still correct since you're getting the same values. It's just a matter of whether you choose to solve for variable x first or variable y first. All right, keep that in mind. Now, on to the second example. This one is a little bit harder, but still not as hard. A farmer has 2,400 feet of fencing. I apologize. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a river. He does not need fencing along the river. What are the dimensions of the field that has the largest area? Again, we're going to be doing the same thing, applying the same concept. First, let's identify the information that we have. First, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a river. He does not need fencing along the river. What are the dimensions of the field that has the largest area? All right, so first thing we need to do is draw this rectangular field so that we don't get too mixed up and you don't have to imagine it in your head. Although, yes, you do have to imagine it. Still, write it down. It's best if you do write it down instead of not write it down at all. Okay, so generally speaking, the perimeter of a rectangle is 2x, all right, 2x plus 2y. Here in this question, it states that he does not need fencing along the river. Let's pretend that the river is going to be alongside one of the y's. So I'm going to cancel out one of the y's. It doesn't necessarily have to be y. You can cancel out any of the sides, whichever you please. You're going to be getting the same answers, all right? With this diagram that we just drew, we're going to be able to write down an equation, a secondary equation, which is going to be, let's count the x's first, 1, 2, so it's going to be 2x plus y, because we canceled this one, so it's going to be 1y, plus y is equal to the value that we have here, which is 2,400 feet of fencing, which is the total perimeter, which is the sum, all right? 2,400. As for the primary equation, if you're wondering whether or not we're going to be using a separate equation for it, no, we're going to be using the same primary equation. The only thing we're going to be doing is substituting p with a. So our second equation, our primary equation, is going to be a is equal to xy, a representing area. All right? We're going to be doing the same exact thing now. With 2x plus y equal 2,400, we're going to be leaving either x to one side or y to one side. This time, I'm going to be leaving y to one side. So it's going to be y is equal to 2,400 minus 2x, all right? We're going to be working with this equation. Once again, we'll be substituting it into the primary equation. So we have a is equal to x times this equation, which is 2,400 minus 2x, which gives us 2,400x minus 2x squared. Now that we have a, we're going to be finding a prime, which is equal to 2,400 minus 4x. And again, the way we found it is by multiplying the power by the coefficient and then subtracting 1 from the power. After that, we're going to be setting a prime to 0. So 0 is equal to 2,400 minus 4 multiplied by x, or 4x, and then using simple algebra, we'll leave x on one side and then find the value of x. So 4x is equal to 2,400, and then we will be dividing both sides by 4, which leaves us with x is equal to 600. This, you can just plug this into the calculator and get the same values. It's okay. All right. Now that we have this, let's prove that we're getting the largest area. Okay? Let's change colors to show that we're switching topics or switching out of like the main solving. Okay? So, again, we're going to be using the second derivative test. So, a double prime is going to be minus 4, because finding the derivative of this, the derivative of 2,400, because it's a constant, it's going to be equal to 0, and then minus 4x, the derivative of x is 1, so minus 4 times 1 is going to be minus 4. Minus 4 is less than 0, which makes it concave down, which means it's going to be a maximum. Great. Now that we've proven that, we're almost done. All we have to do is solve for y. All right? So y, as we mentioned, is equal to 2,400 minus 2x, which then turns into 2,400 minus 2 multiplied by 600, which is equal to 2,400 again, minus 1,200, which gives us the final value of 1,200. Now we have found x and y, and the final answer is going to be, the final answer is going to be the maximum fencing dimension is 600 multiplied by 1,200 feet, okay? So the maximum fencing dimensions are equal to 600 feet multiplied by 1,200 feet. The same values we found for x and y. On to the third example, and this is probably as hard as it gets, and it's still really, really simple. So, this third example states that a square sheet of cardboard with a length of 18 is made into an open box by cutting squares of equal size out of each corner and folding up the sides. Find the dimensions of the box with maximum volume. So, first here, they pointed out that it's a square sheet of cardboard with a length of 18. It's made into an open box by cutting squares of equal size out of each corner and folding up the sides. find the dimensions of the box with maximum volume. So there is going to be proving in this question. Now, so that we don't go off track or get lost, let's draw a diagram again representing this square sheet, all right? So it's going to be a square. And then here they said with a length of 18. Since it's a square, all of its sides are going to be equal. So all of them are going to be equal to 18. And then here it says it's made into an open box by cutting squares of equal size out of each corner. So we're going to cut squares out of each corner in this sheet of cardboard. All right, so usually if we're working with a simple, just normal square, we would be taking 18 as the value itself. But here we can see that each side here is supposed to represent x, all right? And what happened is that we removed an x from the left and an x from the right. So x plus x is going to be equal to 2x, which means instead of it being 18, it's going to be 18 minus 2x per side. Minus 2x, and minus 2x. And when you imagine folding it up, you're going to notice that the height is going to be equal to x. So this is going to be the height. I'll write it down so that we don't forget. Now, you're going to notice that we're going to be finding volume, because here it says find the dimensions of the box with the maximum volume. So we're going to be finding volume, and the volume is going to be equal to length multiplied by width multiplied by height. Here we have length and width being the same equations or the same values. So it's going to be equal to 18 minus 2x multiplied by 18 minus 2x again, multiplied by the height, which we pointed out is x. Now, with this equation, what we're going to be doing is using the distributive method to find 18 minus 2x multiplied by 18 minus 2x, and then multiplying the value that we get by x. So it's going to be equal. V is equal to. What you're going to be getting is 324 minus 36x minus 36x again, plus 4x squared, all multiplied by x. After that, once you multiply each value by x, you're going to be getting, let me switch colors, you're going to be getting 324x minus, I'm going to be doing everything, so 36 minus 36 minus 36, it's going to be minus 72, x times x squared, plus 4x to the power of 3. All right? Once we have this value, we're going to be finding v prime. So v prime is going to be equal to 324. Derivative of x is 1, so it's 324. Minus 72x squared, 1 to the power of 2 is 1, and then times minus 72 is going to be minus 72. 4x to the power of 3. I apologize. After that, we're going to be finding v prime. So v prime is going to be equal to 324, which is 324 times 1, minus 72 multiplied by 2. It's going to be 144. Minus 1 from the power, it's going to be x, plus 4 times 3 is 12, x minus 1 from the power, squared. Once we have this value, again, we're setting it to 0. So 0 is equal to 324 minus 144x plus 12x squared. And you can just plug this equation into a calculator, and you're going to be getting x is equal to 9 and x is equal to 3. So you have two x values. And when you have two x values, you are going to be finding v prime for both and checking which one is a maximum, because there are cases where one is most likely going to be a minimum and the other is going to be a maximum. Okay, so the way we're going to work around this is we're going to find v double prime of 9 first. We're going to be finding v double prime of 9. All right, so v double prime of 9. The way we're going to work around this is we're going to be using v double prime of 9, which is equal to 24. This is a constant in this case. It's going to be 0 minus 144x, so it's going to be minus 144 plus 24x, so 24 multiplied by 9. The final value is going to be 72, which is greater than 0, which means it concaves up. It's going to be a minimum. As for v prime double prime of 3, it's going to be minus 144 plus 24 multiplied by 3. And the value we're going to be getting is negative 72, which is less than 0, which is concave down, making it a maximum. So what we're going to be doing is we're going to be considering v double prime of 9 as a rejected value. We're going to be focusing on the value of 3. Okay? After that, since we found that the x value is going to be 3, what we're going to do is we're going to go back to 18 minus 2x, which is the length, and we're going to be writing this down. So 18 minus 2x, we're going to be substituting the x value with 3, so it goes 18 minus 2 multiplied by 3, which is 18 minus 6, which is equal to 12. After that, we're going to be writing the dimensions. Since we found both the length and the width by calculating this, where we got 12, and we know that the x value is the height, so the x value should equal to 3. That way, we find that the dimensions of this shape are going to be 12 multiplied by 12 multiplied by 3, and that is your final answer. That's going to be all for the lesson of optimization. I hope if you're watching this, you really gained something from it. And don't forget to keep practicing, because practice makes better, although it doesn't make perfect.